Let's talk about acids and bases. But maybe not in the way you learned in school. What if I told you it's all just a simple dance, a constant back and forth between the tiniest of particles, a proton dance that's responsible for, well, almost everything? I mean, we all know lemons are sour, right? That's the acid. But what is an acid, really? Like deep down at the molecular level, what's actually going on? The answer, it turns out, is surprisingly simple. And it all comes down to one little particle. And to get to that answer, we've got to start with one core idea, a simple but incredibly powerful transaction called the proton trade. You know, our modern understanding didn't just pop into existence. It was a slow burn. Way back in 1815, Humphrey Davy figured out hydrogen was a key player. Then in 1884, Svante Arrhenius got closer, focusing on ions in water, but his definition was a little restrictive. It wasn't until 1923 that two chemists, Johannes Brønsted and Thomas Lowry, working completely independently, came up with a brilliant new model that just changed the entire game. And this is the big idea right here. Brønsted and Lowry basically said, forget about just what happens in water. An acid-base reaction is much more fundamental. It's simply the transfer of a proton, a single hydrogen ion, from one chemical to another. That's it. That's the main dance move. So under this new framework, what's an acid? It's crystal clear. A Brønsted-Lowry acid is anything that donates a proton. Think of it as the one that leads the dance, the one that gives something away.
And of course, every good dance needs a partner. If the acid is the donor, the base is its essential counterpart. A Brønsted-Lowry base is any substance that accepts that proton. One gives, the other takes. A perfect pair.
Seriously, if you forget all the fancy terms, just remember this. Acid is the giver, base is the taker. That's the heart of it. That's the whole shebang. Okay, so the proton gets traded, but then what? The dancers don't just disappear off the dance floor, right? No, they transform. And this is where we get to meet our next key idea, the conjugate pairs. All right, let's watch the dance live. Here we have ammonia and water. In this case, water is going to act as the acid, donating a proton. Ammonia steps in as the base, ready to accept it. But look what happens after the proton moves. Poof! The original molecules have become two new things entirely, an ammonium ion and a hydroxide ion. They've swapped roles. Let's break that down. The ammonia, which was our base, accepted a proton. It turned into the ammonium ion, NH4+. Well, now it's holding an extra proton that it could totally give away later on. That makes it an acid. We call it the conjugate acid. And on the flip side, what about the water, our original acid? Well, after it gave away its proton, it became a hydroxide ion, OH negative. Now it's missing a proton, which means it's ready to accept one back. So it's become a base, and we call that the conjugate base. Now, wait a second. You might have caught something a little weird there. Water acted as an acid? But isn't water famously neutral? Well, yes and no. And that brings us to the absolutely fascinating double life of water. This is where we get this great word, amphoprotic. All it means is that a substance can play both parts in the dance. It can be the proton giver or the proton taker, all depending on its partner. And water is, by far, the most important amphoprotic substance out there. And you can see this dual nature so clearly. Mix water with a strong acid, and water says, fine, I'll be the base, and accepts a proton. But as we just saw, mix it with a base like ammonia, and it completely switches gears and acts as the acid, donating a proton. It's the ultimate chemical chameleon. This leads to a really interesting question. If water can be both an acid and a base, what in the world happens when it's just by itself, when it's surrounded by nothing but other water molecules? Who leads the dance then? And the answer is pretty mind-blowing. They dance with each other. This process, where a molecule reacts with itself, is called autoionization. Water is basically acting as both its own acid and its own base, all at the same time. So here's what's happening. One water molecule literally just passes a proton to its neighbor. What you're left with is a hydronium ion, which you can think of as a water molecule with an extra proton hitching a ride, and a hydroxide ion. This is happening constantly in every drop of water, all the time. But, and this is a huge but, we have to understand the scale here. This is happening to a very, very slight degree.
At room temperature, we're talking about only 2 out of every billion water molecules being ionized at any given moment. It's a super rare event, but it is incredibly significant.
Now, this constant, tiny dance might seem like total chaos, but it's not. It's actually governed by a beautifully simple mathematical rule. And that brings us to our final section, finding the constant in the chaos. So much of chemistry is about finding a balance point, an equilibrium. And the auto-ionization of water is a perfect example. It's a reversible reaction that reaches a very specific balance. And that balance isn't random at all. It's a fundamental property of water itself. We measure this balance with something called the ion product constant for water, or Kw for short. The formula looks simple because it is. It's just the concentration of those hydronium ions multiplied by the concentration of hydroxide ions. And the key is, the product of those two is always a constant number at a given temperature. At 25 degrees Celsius, that constant value is 1.0 times 10 to the negative 14th. I mean, that is a ridiculously small number. And that tiny number is the mathematical proof of just how few of these ions are actually floating around in pure water. So this constant, Kw, works kind of like a seesaw. In pure neutral water, the hydronium and hydroxide concentrations are perfectly balanced. But if you add an acid, the hydronium concentration shoots up. To keep the product constant, the seesaw has to rebalance, so the hydroxide concentration plummets. The exact opposite happens if you add a base. This simple, delicate balance is what defines whether any water-based solution is acidic, neutral, or basic. And this little dance isn't just happening in a beaker. It's happening everywhere. It's what allows acidic groundwater to carve out massive sinkholes from limestone. It's the same balance that keeps the pH in our blood so perfectly tuned that we can stay alive. It shows that even the smallest transaction on a molecular level can have massive consequences. Which leaves us with a final thought. What happens when this delicate balance is pushed too far?